Presently, Dr. C.V. Pavankumar sir working in the area of mathematical modeling. Dr. C.V. Pavankumar sir has got good reputation among students for his best way of teaching for the last 2 decades. His simplicity, good attitude, teaching abilities, research capabilities, and presentation skills are additional qualities in him apart from his goodness and vivid experience in the field of education and research. Thank you.
Thank you, Rajeshwari, for your nice introduction about Dr. C.V. Pavankumar Garu. Now I hand over the session to Dr. C.V. Pavankumar Garu. Sir, please start the session, sir.
Thank you, madam. Thank you for nice introduction
Sir, is
about
it audible?
me. Yes, sir. Yes. Am I audible to you, sir?
Yes, sir. Yes, sir.
Thank you, madam. Thank you for nice introduction about me. Let me thank the organizers first of all, but because this is the third time I'm participating in this faculty development program, and thank you for giving me the opportunity. And the today's session is just a fundamentals of linear algebra. It's not a research work, but just what I picked up some of the problems from some of the great textbooks, and I made it into a small notes that I am going to share today. And just it's the fundamentals and how we can think of fundamentals is going to apply in different areas of linear algebra. And me and Acharlu, head of the department Acharlu, we carried out our research under guidance of Professor N.C.H. Pattaviramacharlu, great personality, and his support and clear mathematical approach have greatly influenced us and in understanding the subject, and in many ideas what I share today I learned from him. And he's a giant mathematician in fluid mechanics and mathematical modeling, and he gave the life to the 42 students, and I was the 42nd one. Thank you so much, Acharya Garu, for giving me the opportunity. And I will start my lecture. Okay.
Sir.
Yeah. So this is the lecture on projections and least square problems and QR decomposition. Let me start with what is the basic idea of the projection with a simple two-dimensional problem. I took the vector. This is what we are learning usually. The length of B is root 37. The vector is 1, 6. And we have another vector, A bar is 6, 6. And this A bar is a subspace, right? Because if I can multiply any number, it will stretch. If I'm multiplying with minus, it will flip. If I'm multiplying with 0, it will come to the origin. So this is a subspace of this two-dimensional space. And this subspace is having the dimension 1 because we are moving forward and backward. We don't have a right and left movement on that line. Therefore, this is the one-dimensional subspace of that two-dimensional space. So we are projecting the B bar onto the A bar. Means that's the formula we are learning, A dot B by length of A square times A. So 6 times the vector is, because we are projecting B bar onto the A bar. So 6, 6 is the vector A, B is the 1, 6. We are doing the dot product and we are multiplying with 6, 6. We got 7 by 2 into 1, 1. So what is that projection vector here? This is the projection vector. 0 to P is the projection vector. Actually, the idea is we can't get B from A because they both are having the same, they are not in the same direction. So by multiplying with any scalar of A is multiplying with some scalar, we can't get B because they don't have in the same direction. They are in different directions. Let's see how the same problem we will think with trigonometry. So we are, let's say, assume that there is an angle theta between the A bar and B bar. And we are finding that length x. So that if I am multiplying with that A to x, I will get this projection vector. And B bar is not in the direction of A bar. It is making some error with A bar. that we are calling it as error in least squares, that we will discuss later. So cos theta is equal to this adjacent by hypotenuse x over b. So length of b times cos theta. Cos theta is a dot b by length of a into length of b. So length of b gets cancelled and a dot b by length of a, that is the x. So that x is this length. And what is that projection vector? I am multiplying with the unit vector of a. So unit vector is a by length of a and x is a dot b by length of a. So finally I got into a into, I am writing a dot b as a transpose b. So a into a transpose b into length of a and length, this is the length of a square. It's nothing but a transpose a. So what is this a transpose? Let me discuss that. The idea is the projection. Do we have any matrix to do this activity? Without formula, if I'm having one matrix, if I'm multiplying the vector b with that matrix, I will get the projection vector. So b is multiplied by some matrix. Is it a matrix or not? A is a column, A transpose is a row, and A transpose is the row and column. So column times row is a 2 by 2 matrix. So 2 by 2 matrix, and the bottom is a length 72. So 36 by 72 equal to 1/2 into this matrix 1 1 1 1. Why this came 1 comma 1 1 1 1? If I'm doing R2 minus R1, we have only one pivot element. Therefore, only one pivot column or one pivot row is there. Therefore, the rank of that matrix is 1. Yes, correct. Because this is the one dimensional, we have only one vector about this subspace. That's correct. Okay. And P is equal to 1/2 into, what is this B minus? Okay. So P bar is 1/2 into this one. B is 1/6. I ended up with that. So we are finding one matrix. If I am multiplying with the vector B, I will get the projection vector 7 by 2 into 1 comma 1. So whatever the formula doing, the same thing is done by a matrix. So there is a one matrix which makes the B into the column space of A. So we are projecting B into the column space of A. Because this is more helpful, I can get the projection vector by scalar multiple of A. So that is the idea behind AX is equal to B is not solvable. Yeah, B is not solvable through A. So we are making into the projection of that B into the column space of A. And then we are using that P vector as a representative of the P. That's the whole idea. Let's see this little bit more. What is the geometry here? So geometry part is the error vector is perpendicular to the A. So error vector is perpendicular to the A means this is, let's say the A is a column and this is a perpendicular vector. So columns are perpendicular to the error vector means error vector will be in null space of A transpose. That I will explain little later. See the geometry. So this vector P bar, this is the P bar and this is the E bar. P bar plus E bar is B bar. P bar plus E bar is the B bar and E bar is the B bar minus P bar. Already we know that P is some scalar multiple of A. So E bar is equal to B minus AX. So I know that A bar and E are perpendicular in this graph. See that A bar and E are perpendicular. Therefore, their dot product is 0. Dot product means A transpose E equal to 0. So A transpose E is 0. So I am bringing back that E here. So B minus AX. So A transpose B minus A transpose A times X is equal to 0. So A transpose B is equal to A transpose AX. So X is equal to A transpose B by A transpose times A. So bottom one is the length. So what is P? A times of X. So I am using this X here, right? The X is A transpose B by A transpose A and A is here. So the same matrix we are getting here. So geometry, trigonometry, and some formula, they are all doing the same thing. So A transpose by A transpose A is a matrix. It's a 2-dimensional, 2x2 matrix for this question. So the second thing is, what we know about this projection matrix A transpose A times A transpose by A transpose A. It's a projection matrix. Is this matrix is symmetric or not? So let's do P transpose. So A transpose by A transpose A and whole transpose. So transpose will be in the reverse order. We got A transpose transpose and A transpose by. This is a number. We don't have any transpose for that. We can write the same thing. And we are ending up with A times A transpose by A transpose A. We got the same thing. Therefore, P transpose is equal to P. So every projection matrix is symmetric. So another thing is, if I'm stretching this vector B, to the double time, the projection vector is also double. That is one thing. If I'm doubling this vector A, the projection will be the same. Because we are not stretching B, we are stretching A in the second case. If I'm stretching B bar, the P bar will stretch. If I'm stretching A bar, the projection vector will not stretch. So what is P square? If I'm doing double the time projection, if I'm projecting B onto the A, we are end up here. If I'm doing one more time, we will be there. We are not moving further. So if I'm doing the projection double the time, we will get the same thing. See, let's see that P square is what? So P square is A transpose by A transpose A, again A transpose by A transpose A. By associative property, A transpose times A, that makes into a length. So I'm cancelling one length, A transpose by A transpose A. Again, we got the P. So P square is equal to P is an idempotent matrix. So let's see from the last example, P plus E is equal to B bar. E bar is what? B bar minus P bar. So 1/6 minus 7 by 2 and 7 by 2. We got minus 5 by 2 and 5 by 2. 5 by 2. It is establishing the condition that E is orthogonal to A. So always the error vectors are perpendicular to the columns of A. That we will do later. The whole idea of the projection, B is not in the direction of A. So we are bringing the representative of B in the direction. That representative is called as projection vector. Instead of B, we are using P. So the AX is equal to B is a linear system, which is not solvable. Therefore, instead of B, we are using this representative vector P because that is there in the column space. If it is in the column space, we can build up a linear combination of columns. So it is solvable. That's the whole idea. So E bar lies in, because E bar and A bar are orthogonal. So E bar lies in null space of A transpose. That I will show the diagram later. Let's work with higher dimensions. So when AX is equal to B, we don't have solution because B is not in the direction of columns of A, or B is not a linear combination of columns of A. And we have more equations than unknowns, and we can't solve them. We are looking for the closest solution that we can solve. So that closest one is the main idea in the linear regression, because the closest distance is the minimizing the error concept. So AX, what is AX? A times X is always linear combination of columns of A. That will be there in the column space of A. AX is in column space of A. B is not in the column space of A. Therefore, AX is equal to B is not solvable. So instead of B, I am picking up P, where P is a projection of B in the column space of A. So how to get that everything into matrix notation? What we did in one-dimensional case, that is A transpose by A transpose A, we have to get the same idea for the higher dimensions also. So for that purpose, I'm choosing a plane. That plane is a column space of, it is generated from the two basis vectors u1 and u2. So the plane is generated by linearly independent vectors because they have u1 and u2 have different directions, therefore they are linearly independent. I am calling it as u1 is the vector u1 I am putting in the first column, u2 I am putting in the second column. They are linearly independent. This condition is so important. Columns are linearly independent, but not rows, not necessary rows, because we have more equations than unknowns. So the plane u1, u2 could be n columns. If it is has n columns, no problem. But all the columns should be linearly independent. So if B is not in the column space, we are taking its representative P in the column space. If it is in the column space, P bar, P vector, P projection vector, I can write it as a linear combination of basis vectors. That's the whole idea of linear algebra. If it is in the given subspace, I can write it as a linear combination of basis vectors. So P as x1 hat times u1, that is the number I am stretching u1. This is the number x2 hat is the number I am stretching u2, and combining that so that we are reaching the vector P. So I can write it as a dot u1 u2 matrix, and the column is x1 hat and x2 hat. The meaning of that is right mixture of u1 u2 so that we will get the P. That's the whole idea. So error is, this error vector is b bar minus p bar, which is perpendicular to the plane. So b bar minus ax is perpendicular to the plane, means perpendicular to the column space, means perpendicular to the all columns of A, or perpendicular to the each basis vector, because the whole plane is generated from the basis vectors, right? So E bar is perpendicular to the basis vectors. So the basis vectors are u1 and u2. Their dot product is 0 because they are perpendicular. Dot product means u1 transpose times, because always dot product is A transpose B, like that. So u1 transpose times B minus AX. This is so important, these two equations. What does this is giving the, see, u1 transpose and u2 transpose are the rows, because u1, u2 are the columns, u1 transpose and u2 transpose are the rows, and B minus AX is equal to 0. Means u1 transpose and B minus AX is producing 0 vector. u2 transpose dot product is producing 0 vector. So A transpose B minus AX is equal to 0. So multiply that, A transpose B minus A transpose AX is equal to 0. And A transpose AX hat is equal to A transpose B. Therefore, X hat is equal to A transpose A inverse into A transpose B. That is the X hat. That is the number. That is the sequence of numbers. These are, X hat is the sequence of numbers. So these numbers, we are mixing up the basis vectors of A so that we will get the P. So what is the definition of P? A times X hat. In place of X hat, I am writing this whole thing. A transpose A inverse. A transpose A whole inverse into A transpose B. So if I am writing in the place of X hat, see that is the matrix. A times A transpose A whole inverse times A transpose. This is a matrix. We have the same thing in one dimensional. See that A transpose B. So this one, projection matrix. A transpose, bottom is A transpose A. Because in multi-dimensional, just we are writing this inverse in the between of these two numbers. So we got the same formula. One more time. A times A transpose A whole inverse times A transpose is the projection matrix. That projection matrix is multiplying the vector which is not in the column space. That we are getting the projection that will be in the column space of A. So the same thing in one dimensional, just this is a number. Instead of number, we are writing A transpose A inverse here. Okay. So we got the projection matrix in higher dimensional as A times A transpose A inverse times A transpose. So let's check that same thing whether P square is I here, or can we do, can I expand this inverse here? Do I need to do or not? If I'm doing the inverse, if I'm doing the inverse A inverse, because inverse will be in the reverse order, in A transpose whole inverse. But A transpose whole inverse and A transpose is here. So these two will become an identity, these two will become an identity. Is P is I? No, something wrong here. Why? We should not do this. We should not do inverse because we are only columns are independent, not rows. So this doing A inverse does not, we should not do that. So this is not allowed because A is not a square matrix. We have more rows than columns, more equations than the unknowns. So if it is a full set of independent columns and if it is a square, then P will become an I. If P is I, then if P is I means what? P is I means the whole space we can get that, so it is invertible. So the connection is very important between these two. P is not invertible here. Let me see that whether it is correct or not in the first case. We got some P in the first page. See that P is 36, 36 and 36, 36. It has rank 1. It is not invertible. It is not in P is not invertible. Yeah. And let me see that. Okay. A is having only independent columns but not rows. So P transpose is P because in the one earlier also we did P transpose is P and P square is equal to P. We have to establish that again. So P square is the same projection matrix I am writing 2 times. So A transpose A whole inverse times A transpose. A into A transpose A whole inverse into A transpose. So by associative property, I am mixing up these two, A transpose A. So A transpose A and A transpose A whole inverse, that becomes I. I'm ending up the same thing, A transpose A whole inverse times A transpose. So P square is equal to P, and P transpose is because transpose is A transpose is A comes here, A transpose will come here. That will be fine. P transpose is equal to P. So B bar is not a vector in the column space of A. The whole idea is we are bringing that B bar into the column space of A. Okay. Now, if B bar is in column space of A, what will happen? If B bar is in column space of A, what we will get? And when we apply a projection to that, B bar in the column space of A, so B bar is the linear combination of columns of A, right? So if B bar is in the column space, I can create a B bar from the columns of A. So B is a linear combination of columns of A. So B is equal to, I can write it as AX. So X are some numbers making the vector B bar from the columns of A. So I'm plugging, because PB is B bar. Earlier we saw that. P projection matrix applied to the vector B, we will see that what will happen. This is the special case if B bar is in the column space of A. Earlier B bar is not in the column space of A. A times A transpose A whole inverse times A transpose AX. Again, I am using this, I am changing the brackets here, associative property. A transpose A. A transpose A inverse and A transpose A is I. So it will become AX. Again, AX is equal to B. So two different cases. So if B bar is not in the column space, we are looking for P projection vector. If P bar is in the column space, no problem, PB is equal to B. If some vector, see that, if some vector in column space, we can get it by linear combination of columns of A. Just to show that example, I wrote one small example here. 1, 2, 3 is one column, 3, 4, 5 are another column. These two columns are independent. And I am writing that 5, 8, 11. Do we get this 5, 8, 11 from these columns? So if you plug in place of first one, 2 and 1, so if you are mixing up these two columns, 2 times of first column and 1 time of second column, we will get that. 2 and 1 time of 3 is 3, 5. 2 times of 2 and 1 time of 4 is 8. 2 times of 3 is 6 and 1 time of 5 is... So if we have a linear combination, B is fine. If B is not in the column space, getting these numbers is difficult, then projection matrix will help, because I want the representative of B in the column space. That representative is P bar. If B bar is perpendicular to the column space, what will happen? If B bar is perpendicular to the column space, if the B bar is perpendicular, then it will be in the null space of A transpose, because null space of A transpose and column space are perpendicular to each other. That's the fundamental idea in linear algebra. Column space of A and null space of A transpose are perpendicular to each other. So I'm picking up, if B bar is perpendicular, B bar should be in the null space of A transpose. So PB will become 0. Let's see that. P is this matrix, A transpose A inverse into A transpose B. Again, I am using the associative property, A transpose B. But I know that A transpose B is equal to 0 because if B is in the null space of A transpose. If the vector is in null space, if you are doing the multiplying the A transpose, it will bring up to 0. So 0 times of that matrix is 0. So B bar is perpendicular, that is in the null space of A transpose, then the projection will become 0. If B bar is in the column space, it preserves the B bar. If B bar is perpendicular, it kills the B bar. Okay, this is the whole idea of subspaces. There are 4 subspaces in linear algebra for any matrix which maps from R power n to R power n. Means if I am taking an n-dimensional vector and multiplying with n, we are landing up within the M space. So this is the row space whose dimension is R. This is the column space whose dimension is R. That is the one theorem in linear algebra. Row space and column space both have same dimension of the dimension is rank R. So if row space is always perpendicular to the null space, so perpendicular to the null space means if R and this dimension is n minus R, because sum should be n and here sum should be m. Therefore, the null space of A transpose and column space of A are perpendicular to each other. So null space of A transpose is having the dimension of m minus R, or there is another name called as left null space. So this is the very important diagram of linear algebra. Columns, the whole idea of what we are discussing on the right side now. Because the B bar is in perpendicular, B bar should be here. So A transpose B is equal to 0. So this is the general case. First 2 cases what I discussed here, B bar is in the column space, B bar is the perpendicular to the column space. Now B bar is in, it's making some angle with the column space. So it has the component, vertical component and horizontal component. So from the earlier, these 2 cases, this is the projection matrix preserves this. The projection matrix kills this. If anything is perpendicular to the column space, it kills. PB equal to 0. Earlier we did that. PB equal to 0. So what is the whole idea of the projection matrix? Is the general vector B bar, if it is having the 2 components, vertical component and horizontal component, it preserves the horizontal component and it places as a projection vector. And this, we are killing that component perpendicular to the column space of A. That is the whole idea of the projections. P kills the perpendicular component and P preserves the component in column space of A. So we are getting this one, we are killing that one. And let me take one simple example of linear regression problem. Let's see how everything will come into nicely. I'm taking 3 points, 1, 2, 2, 5, 3, 3. So there are in different positions. They are not on a line. There is no line passing through all these 3 points. Actually, I can draw infinite number of lines, but one is the best line is there, which minimizes the. That's the whole idea of the least square regression. So I'm taking 2 points, 1, 2, 2, 5, and 3, 3. So let's see how all these helps in line of best fit. We are looking for best fit. No line goes through all these 3 points. The best means overall error is small. I will explain this diagram a bit later. So overall error is small. So if the error is small, we will get the best fit. That best fit will give you the slope and y-intercept of that. So I am choosing this equation as C plus dt. If I am plugging this point, I will get one equation. C plus d is equal to 2 because y value is 2. T value is 1. I am plugging here because C plus dt. C plus d equal to 2. C plus 2d is equal to 5 and C plus 3d is equal to 3. Definitely we don't have solution for this because we have the columns 1, 1, 1, 1, 2, 3 and 2, 5, 3. We don't have solution but the important thing is these columns are linearly independent. How can we say these two are linearly independent? If you are doing R2 minus R1, R3 minus R1, both the columns will have pivot elements. Therefore, we can say the two columns are linearly independent. That I am not writing here. Just we can say that two columns are independent. Okay. They have, for sure, that they have different directions. Not necessary to be perpendicular. If they're independent, that is enough in this case. If they are perpendicular, that we will see later. Column space of A does not include this vector B. So instead of B, I am picking up the projection. So let me explain this. So this is the vector B bar we are taking. Its projection is P bar, that is in the column space of A. B bar projection is P bar. And the error between these two vectors, P bar plus E bar is B bar, right? P bar plus E bar is B bar. So E bar is B bar minus B bar. So this is the error vector. This is also error vector. See, the error vector is a null space of A transpose because these two are perpendicular. The same thing we discussed here. So the error vector is always in the null space of A transpose. Let me explain that. So the question is, P bar is the projection of B bar. Is E bar is also a projection or not? Yes, it's also a projection of B bar into the null space of A transpose. So how can we get that? So P bar plus E bar is equal to B bar. P is what? The vector P is multiplying the projection matrix with the B bar, we will get the P bar. PB is P bar. So PB plus E bar is equal to B bar, and I am putting on the other side. So B bar minus PB bar. So I am taking this B bar as common, I minus P is equal to. So this is also one kind of projection. Error is also one kind of projection. Original projection vector is also a projection of B bar. Both are coming from projections. So if you are doing the projection onto the null space of A transpose, we will get the error. If you are projecting the B bar into the column space of A, we are getting the normal projection. So P is symmetric. Therefore, I minus P is symmetric, no doubt. P is idempotent, we did that. I minus P is also idempotent, and P square is equal to P. So projection onto the perpendicular space is E bar. That is the one of the best idea. We'll see all these through these calculations later. So we have three equations, and we have two linearly independent columns. Column space of A does not include this vector B. Therefore, error is equal to AX minus B. So let me explain one more diagram, this geometry. So we have these 3 points, right? We have these 3 points. In that 3 points, we have whole information here. See that this is the original data point B1. But on the line, we have P1 because we are bringing the vector B onto the line. That is the in one-dimensional space. Earlier in the first page I explained. So B bar we are bringing onto the line. That is the projection vector P1. So the dots, those are in P1, P1, P2, P3 are projections of B1s. So the distance between B2 and P2, B1 and P1 are the errors. So we need to minimize these errors. So that minimization will help us in finding the line of best fit. So minimizing means the distance means the length, right? So E is equal to AX minus B. Why I am writing AX minus B? Because E is P minus B, P is AX. Yeah. And what minimizing the errors means we need to taking the lengths, E1 square, E2 square, and E3 square. That is the sum of squares of errors, which is never negative quantity. If some points is very, let me explain something which is very important in statistics. We call it as, if some point is very far, let's take one point here at 0. At 0, we have some point at somewhere here. So if the point is somewhere here, the error is more, right? So it dominates all these 3 errors. Therefore, that point is called as outlier. So most of the times, all softwares, they will remove the outlier and they will consider the maximum data. They will leave some of the data which is very far away from the group of data values. So it will take off. So the outlier is very far. If it is making higher error compared to all these, we are neglecting that. That we are calling it as outliers. So then this line of best, so if it is creating error, more error, this line will not be like this. It will shift. It will tilt to the another direction. So because the big error will add up on the previous error group, that point is called the outlier. So what is this P1, P2, P3 in this diagram? What is this P1, P2, P3? How we will get that? By plugging these numbers, right? So if I plug that numbers, P1, P2, P3, they are on the line. So instead of original points, which is not solvable, 2, 5, 3 on the right hand side, we are picking up P1, P2, P3 numbers. So then the system is solvable. So that already we explained earlier. So instead of the B, we are choosing the projection vector P1, P2, P3. Because P1, P2, P3 is available in the column space, I can get from the linear combination of columns. We get it by doing the linear combination of columns. Let's say that X hat is C and D, some numbers. So this is the equation for the, already we did that, A transpose A times X is equal to A transpose B. That's called as normal equations. So A is 1, 1, 1, 1, 2, 3. Therefore, A transpose will be this one. A transpose is this one. A transpose A. And then on the right hand side, A transpose B. This A transpose B, which is symmetric, very, very important. This is A transpose B is symmetric and it is invertible. And we also call it as in positive semi-definite. Positive semi-definite means eigenvalues and eigenvalues are positive numbers and sometimes it's 0. So we got A transpose B, right? 1021 A transpose. This is the A transpose A. This is the A transpose A. I'm doing 3664. A transpose A is 366. So A transpose A, what is the special about A transpose A? What is the special about A transpose A? A transpose A, if some vector is in null space of A, let's say AX is equal to 0, A transpose AX is also 0. Means A transpose A and AX both have same null spaces. If null space is 0, then both are invertible. A and A transpose A. That's very, very important. We will use the concept in pseudo inverse. That we will come to later. So A transpose B, I am doing the right hand side here. That is 1021. So these are the equations. A transpose A times CD equal to 1021. So these are the two normal equations. By 3C and 6D is equal to 10. 6C and 14D equal to 1021. These two are called as normal equations. So we can get these normal equations from calculus also. I think what is even? Even is C plus D minus 2. It is coming from here. Where is, yeah, C plus D minus 2 is the error. C plus 2D minus 5. C plus 3D minus 3. These are all the errors, right? So squaring the errors and do the partial derivatives of these errors with respect to C and D being 0, making that equal to 0, we will get the same. I'm not doing that, but just we can get it from calculus also. But why this calculus and linear algebra is giving the same equation? See that if you are doing the derivative 2 times of that, it will become a linear. It will become a linear system. Even though it's a square, doing 2 times of, if I'm doing the derivative with respect to C, you will get 2 times of C plus D and C derivative is 1. It will come to the linear equations. So that's why linear algebra is more friendly than calculus. So we got that. I'm tagging this because I'm solving these 2 equations. I'm writing on the augmented matrix. So do R2 minus 2 R1, R2 minus 2 R1. So 0 to 1, right? So 2D is equal to 1 because this column is we are multiplying with C hat, and this column we are multiplying with D hat. So 2 times of D hat is equal to 1 or D equal to 1/2. What is D? D is the, what is D in the equation? D is the slope and C is the y-intercept. So we will, by solving this equation, 3C plus 6/2 is equal to 10, C is equal to 7/3. So C hat and D hat is 7/3 and 1/2. I am plugging back in the lines because C plus dt, C is 7/3 and 1/2 t. What we discussed earlier, P1, P2, P3 are the points on P1, P2, P3 on the points on line, right? So if I'm plugging t equal to 1, so 7/3 plus 1/2, so this will become 14 and 17/6. If I'm plugging t equal to 2, that will be 20/6. If I'm plugging 2, 20/6. If I'm plugging 3, 23/6. See that? This is the important diagram I'm looking for. P1, P2, P3 are on the line by plugging t equal to 1, t equal to 2, t equal to 3. So we got that vector. That is the projection vector. So what is another observation? Earlier we discussed B bar minus P bar is E bar. So what is the B bar? B bar is the original vector on the right hand side, 2, 5, 3. P bar is 17/6 minus 20/6 and 23/6. We are getting error is minus 5/6 and 10/6 and minus 5/6. So I got E bar. So E bar and P bar are perpendicular or not? Yes, because P bar is in the column space, E bar is in the null space of A transpose. They have to be perpendicular. See that if I am doing that, you will get 0. That's the one thing we discussed, the fundamentals through the problems. And P bar is in the column space, right? P bar is in the column space. So E bar is perpendicular to the column space means E bar is perpendicular to whole column space means first column also these are the basis vectors for column space. So E bar perpendicular to this vector also, and E bar is perpendicular to this vector also. Let me check that. E bar is minus 5 by 6, 10 by 6 and minus 5 by 6, and take that 1, 1, 1 vector. That is the easiest way. So do dot product, you will get 0. So E bar is perpendicular to the column space. Yes, that's we checked. Let me go through some of the other interesting things. P is a projection matrix. A transpose A whole inverse times A transpose. A is this matrix. A transpose is I am writing. And already I got A transpose A is equal to that 3, 6, 6, 14. And I'm taking the inverse of that. So I multiplied. I got some vectors, right? P. Yeah, P is this is the projection matrix for this case. If I'm multiplying projection matrix with B, we have to get P. Let's check that. Earlier we did P1, P2, P3 is the projection vector. Are we getting that or not by doing PB? So P is the matrix, B is the 2, 5, 3, pi 6. If I'm multiplying that, 10 by 6 and something like now 5 by 6 is 10 by 6, 15. Yeah, we'll get that. Because this is minus 3 by 6. So 17 by 6 and 20 by 6 and 20 by 3 by 6, we got the P. Same P is here. See that 17 by 6 we got from the line. PB, so projection matrix times B is projection vector. We are getting that also. And what else we have? What else? So I minus PB. What is I minus PB? Is error vector. So I is 3-dimensional identity matrix. I got P is this matrix, projection matrix. I subtracted. So 1 minus 5 by 6 is 1/6. 0 minus 1/3 is minus 1/3. 0 minus of minus 1/6 plus 6. Like that I did. And because B is 2, 5, 3, I plugged it. And I'm multiplying these two matrices. I end up with minus 5 by 6 and 10 by 6 and minus 5 by 6. Again, see that E bar is what? We did E bar is equal to B bar minus P bar. We got minus 5 by 6 and 10 by 6 and minus 5 by 6. I'm establishing this diagram thoroughly. This one. I minus PB is I have to get the error vector. Yeah, that's the I minus PB. PB is P. I minus PB is the error vector. Instead of solving AX is equal to B, I'm plugging AX is equal to P. 7 by 3. X hat is 7 by 3 and 1 by 2. Where is this X hat? 1 by 3. Yeah. What linear combination we are looking for, right? See that C hat and D hat is 7 by 3 and 1 by 2. So taking the linear combination of C hat and D hat here, 7 by 3 times of first column, first 1 by 2 times a linear combination of columns will end up with P. So completely established. So all the fundamentals what we are seeing through the graphs, the P1, P2, P3 vectors are on the line, errors are perpendicular, and P minus B bar is error, and I minus P times of B is the projection vector that is into the null space of A transpose, and P times of B bar is the projection vector on the column space. everything is satisfied through this example. That's the one of the best ideas. What else we have? This is very important. Two-sided, left and right, and pseudo inverses. So this is the big picture of linear algebra. Row space is the whose dimension is R, and column space. So let me explain this. If I'm taking one vector here and I'm multiplying with A, what vector we will get? And where we will get that vector? A times X. A times X means it's a linear combination of columns of A. So linear combination of columns of A will be there in column space. So AX will be here, right? So just I'm giving some A is M by N matrix, A transpose is N by M. Later I will explain how we have to use this. So the whole idea of this topic is two-sided inverse, left inverse, right inverse, and pseudo inverses, right? What is that? What is the beauty of the two-sided inverse? Two-sided inverse means if I am writing on the right side or if I am writing on the left side, so A inverse is equal to I and A inverse A is equal to I. That's it. When we will get that kind of inverse in the problems. If A has full set of pivot columns and A has full set of rows, pivot rows, and it's a square matrix, right? So what is the link between R, M, and N in that case? Let me explain one more time. I am thinking of if the matrix A has two-sided inverse, like A inverse is equal to I, or A inverse A is equal to I, that will happen for the square matrix, and we have full row pivot rows and pivot columns. Means M pivot rows and N pivot columns, that is equal to rank. So M is equal to N is equal to R. In that situation, we have two-sided inverse. So M is equal to N is equal to R. What does it mean M equal to R equal to N in this diagram? So R is M. So R is equal to N here. So this null space is gone. In that situation, if we have two-sided inverse, we don't have null space for A. We don't have null space for A means what? We don't have free columns in A. Because we are saying that A is linearly, all columns are linearly independent, right? And we are saying that R is equal to M. R equal to M means this null space is knocked off because there is no vector. Its dimension is 0. No basis vectors are there. The definition of dimension is number of basis vectors, right? So if the dimension is 0 means there is no vector to make if I'm multiplying the matrix and it is not going to the 0. That is the meaning of two-sided inverse. So when the matrix have two-sided inverse, null space of A is 0 vector only. Why 0 vector? See that there is a common vector 0 vector. If nothing is there means 0 vector will be there. Why? Let me go through that little more detail. All columns are linearly independent means, so which combination will make it into a 0 vector? Only 0, 0, 0, right? That's why null space has only 0 vector. So null space of A transpose is also having the only 0 vector. If non-zero vectors are there, then the dimension will be some number. That's the complete details of, I think that's fine, right? And then, yeah. So when we have two-sided inverse, these two null spaces are knocked out. We don't have that null spaces. Okay. What is the second situation? When will we have left inverse, right? What is mean by this left inverse? We will see that. So that inverse only works on the left side. Right side, it is not good. That works only on the left side. When will this situation will come? So we don't have full rank, but we have column rank. Column rank means what is the rank? R is equal to n, right? Because full columns or n columns are there because matrix is m by n. We are saying that all columns are independent. All columns are independent means all columns are having the pivot numbers. There is no free columns. So R is equal to n. R is equal to n, but that we have more rows. More rows. This situation is there in this case, right? We have more rows. So that we have more rows, but two columns are independent. This is the situation. We are, say, it's connecting. Everything is connecting. So see that this is the more, we have these two columns are independent, but not rows are not independent. Let me come back to that. Yeah. We don't have full rank. Full rank means full column rank, full row rank is full rank. But we have full column rank. Means R is equal to n. R is equal to n means what in this diagram? R equal to n means this one, right? This is knocked off, but this is there. So in left inverse, null space of A is knocked out, null space of A transpose will be there. Because what is the n is equal to R, right? N equal to R. So n equal to R means R minus R, because if you plug that n equal to R here, R minus R equal to 0. This is knocked out, right? So there is no vectors in the null space of A for the left inverse case. Independent columns, no combination of columns will give 0 except 0 vector. See, this one I'm talking about. No null space, 0 null, only 0 vector is there in the null space. Let me see that. Then the system AX is equal to, how many solutions will be there in this case? AX is equal to B. Because all columns are independent, and if B is in the column space, I will get the solution. If B is not in the column space, I can't get the B from the linear combination of columns of A, so we don't have solution. So two situations. One situation is B is in column space of A, we have solution. B is not in column space of A, we don't have solution, right? So either 0 or 1. That's the one case. So has one solution or none. That's the B is in column space of A, we have a solution. That is the condition very, very, very important in concept of linear. Condition is very important in least square problems. Then A transpose A is symmetric and invertible. Yeah, you see that? I did that here. See that A transpose A is invertible. Here I wrote. Because why? Because columns are independent. The columns are independent and more rows are there. A transpose A is good. A transpose is bad. Yeah, see that. A transpose A is symmetric and invertible. So we can get the inverse of this. Let me tell you, this is the more important thing. A transpose is, that's why I wrote some thing here to make it little easier if you are seeing the notes, right? A transpose is n by m, A is m by n. If I multiply that, we will end up with n by n. Yes, we are fine now because the n columns are independent. N by n is okay because it is invertible. That's the whole idea. A transpose is not good here. Let's do that. A transpose. What will happen here? A transpose. A transpose will come here. That will m by m. M rows are not independent. some free variables are there in the rows. So it's not invertible. So when columns are independent, A transpose A is good. That is invertible. So A transpose A has inverse, no doubt. That must be why you are writing on the left side. A transpose is invertible. We are saying earlier, we are saying that, let me see that. A transpose is invertible. So A transpose having the inverse, because we have to end up with identity matrix of n, because n columns are independent. If you are writing the whole setup on that side, that will not work. Always independency is very, very important, because we are saying n columns are independent. I want identity of n. So we have to write on the left side, A transpose A inverse. So change this into A transpose and A transpose whole inverse I am taking into A1 matrix. That matrix is the left inverse of A. That matrix is left inverse of A. One more time, maybe some confusion is here. A transpose and A transpose whole inverse, I am writing on the left side, and combine these two matrices, that is, whole thing is called as left inverse of A. What will happen if I am writing on the right hand side? This whole thing, if I am writing on the right hand side, earlier we saw that this is the projection matrix of column space of A. Earlier we did that very first here. What is that? Yeah. Very first, I think. Okay, yeah, I see that P is A transpose whole inverse. We are writing on the right side. If you are writing, when the columns are right independent, if you are writing that matrix on the right hand side, it will become a projection matrix. If you are writing on the left hand side, that will become a left inverse. That's the very important thing. Next, yeah. But the very important thing is projection onto the column space of A. That's more important. And what is right inverse? So left inverse is, we are talking about the left side of the diagram. Right inverse, we are talking about the right side of the diagrams of 4 subspaces. So if A has full row rank but not column rank, all columns are not independent. All rows are independent here. So rows are independent means all rows are having pivot elements. So what we can say about columns? How many solutions of AX is equal to B? So all rows are fine, but not columns. Means some columns, they don't have pivot elements, right? Like rectangular more width matrix is there. Number of columns are high. So that number of columns are more, but less number of rows. All rows are fine. They are linearly independent, but not columns. That means some columns are having free variables. So there is a null space, right? So what is that case? R is equal to M. R is equal to M. So this null space is knocked out. This null space is knocked out. Earlier, in this case, we are knocking out this null space. So R is equal to M. So what is the R equal to M, right? Okay. What is the null space of A now? If R is equal to M, null space of A. R is equal to M, null space of A is N minus M. So your null space of A is not empty now. It has some basis N minus M, means N minus M vectors are there in the null space of A. So if null space is having some vectors, what will happen? If null space is having some vectors, multiplying with A will goes to 0. We can't invert them, because from 0 we can't invert, right? So null space of A is equal to N minus M free variables. So we will have infinitely many solutions. Why infinitely many solutions? Because free variables are there, and any solution is particular solution plus null solution, x of x null plus x particular, right? Any solution of Ax is equal to B is x null plus xp. We have so many x nulls here. So we have infinitely many solutions. So in this case, A transpose is fine. Earlier A transpose A is fine. Here A transpose is fine. A transpose A is not good. See, if I'm multiplying that, so A transpose is fine means there is an inverse for that. So if I'm writing on the right hand side, A transpose and its inverse. But I am mixing up these two by using associative property. See that we are getting the identity matrix of M because rows are independent. That's why I'm getting I M by M matrix. So if we are writing this inverse on the right hand side, what we are writing on the right hand side, if we are writing on the left hand side, what will we get? That's also a projection vector into the row space. Earlier we have projection. If I am writing, this is good. If I am writing inverse, we will get the projection matrix onto the column space. What is the same thing here? If you are writing on the left side, we'll get the projection vector, projection matrix onto the row space. This is another general case. What is this one? Pseudo inverse. Pseudo inverse is we don't have. Yeah, pseudo inverse is R is equal R less than M and R less than N, right? So number of rank is less than number of rows, rank is less than number of columns. So there are M minus R free columns in A transpose and N minus R free columns are in A. So your null space is not empty, null space of A transpose is not empty. So some vectors are there multiplying the columns and making into zero. Getting back that information is very difficult, right? Because if you are knocking to zero, if it is knocking to zero, getting back the information is very difficult. So if you have free columns, giving that free columns are, that free variables are giving the trouble to get the inverse, right? What is there? Because of matrix takes a vector and gives the zero vector, then bringing back the original vector is difficult. So then pseudo inverse will exist. What is that pseudo inverse? Do we have any relationship between row space of A and column space of A? Yes. Their dimension is same. Dimension of column space is R. Dimension of row space is as equal to R. This is the very, very, very important behind the pseudo inverse. So pseudo inverse, what is doing pseudo inverse? Ax is equal to, earlier I said, A multiplying with any x vector that will land up into the column space. Take another vector in row space, Ay, it will land up into Ay into the column space. Is Ax and Ay are equal or different? That's the question. Do we have same vector or they are different? I mean, the question is, if x is equal to y, Ax is equal to Ay, or x and y are different, Ax and Ay are different. That is the question. That's what we are checking now. We are checking 1-1 mapping. If we are establishing 1-1 mapping, inverses exist between these two spaces, right? See how we will get that information, something we will discuss later. So do we have 1-1 transformation here, 1-1 mapping? Let's take that. Let's take Ax is equal to Ay. So Ax is equal to Ay. What is that? Ax is equal to Ay. So take A common here. On the left side, x minus y equal to 0. So A times something is equal to 0. What is that? A times something is equal to 0. Therefore, this vector is in null space, right? So x minus y in null space. But we are saying that x and y are in row space and X minus Y is also in null space because linear combination of vectors, because X minus Y, if two vectors are there in one subspace, because that is the important property of the subspace, right? If two vectors are in the subspace, if their addition or subtraction or scalar multiplications will be in the subspace. So we are taking X and Y are two vectors. X minus Y will be in the row space, but this is saying X minus Y in the null space, right? If something is equal to 0. So X minus Y is in the null space. X minus Y is null space means which vector is common to both? Only 0 vectors. Therefore, X minus Y equal to 0. Therefore, X is equal to Y. So AX is equal to AY, X is equal to Y. Means if I am taking two different vectors, it will land up into two different vectors. If they're equal, these two are equal. So we are establishing the 1-1 mapping. If 1-1 mapping is there, there is an inverse. That inverse is called as pseudo-inverse. Pseudo-inverse exists only between these two spaces. How pseudo-inverse we are going to get that? So pseudo-inverse is usually there is some other name for that, Moore and Penrose pseudo-inverse. There are two mathematicians, Roger Penrose and E.H. Moore. American mathematician, I think he's a German. AX is equal to B is the linear system, right? So what is the pseudo-inverse of that we are looking for? So let me explain how pseudo-inverse we will get that. How can we get the pseudo-inverse? So any matrix A m by n can be written as three products like, what is this? SVD, singular value decomposition, right? U is a orthogonal matrix, sigma is a diagonal matrix, and V transpose is also an orthogonal matrix. Orthogonal, diagonal, and orthogonal. See how everything is connected to the SVD. Projections, what we are establishing in projections and left inverse and right inverse, that projections will help that. And if you want the inverse between the two subspaces like row space and column space, because 1-1 mapping is there between the two spaces. So U sigma V transpose, U is, if A is m by n matrix, U is m by m, n by n, sigma is m by n. See that this is m by m. M rows are, this is orthogonal. In SVD, in singular value decomposition, these two are orthogonal. Orthogonal means what? Orthogonal matrix. Orthogonal matrix, all columns are perpendicular to each other. Perpendicular to each other means they are linearly independent. They are linearly independent means they are invertible. So these two are fine. Because this is also orthogonal, this is also orthogonal. So inverting them is not a difficulty thing. What is the inverse of that is the transpose, right? So because they are orthogonal matrix. The definition of orthogonal matrix is U transpose is equal to I and V transpose is equal to I. So orthogonal means rotate, stretch and rotate. Okay, what is U? What is U? Is coming from the eigenvectors of A transpose. See that? This is linked to this pseudo inverses. A transpose A, A transpose A works in when columns are independent. That's why we are getting, where is N here? N is here, A transpose A. M is here, A transpose. So U is the eigenvectors matrix for A transpose, and V is having the eigenvectors of A transpose A, and these are the singular values. How we will get the singular values? I think the eigenvalues of A transpose A. AX is equal to B. AX is equal. I will give one example. AX is equal to B, but A we are writing into A we are writing into U sigma V transpose, that is SVD, multiplying with U transpose on both sides, U transpose B, because U transpose U is orthogonal matrix, therefore that will become an I. So sigma V transpose X is equal to U transpose B. Again, I am multiplying with sigma inverse. Hold on. Sigma inverse, right? We'll see that. We'll come back to that. Why we are writing sigma inverse? Sigma inverse into sigma is I. I am multiplying with V on this side. Just I am removing each one. Here I transpose U transpose. I am taking U transpose. Then I am taking sigma inverse. The question is, what is this sigma inverse? That is the pseudo inverse. That is the pseudo inverse, because we do see that. What is the see, we have some rows are zeros are there. So what is the determinant of that matrix is 0. It is not having the inverse actually, but we are taking that inverse as that's the pseudo inverse is doing. That's the pseudo inverse is doing. So what does P pseudo inverse is actually? We multiply left, we are getting the identity. If we are getting multiply on the right, we get the identity. If we are getting projection onto the column space of A and rows, what is pseudo inverse is doing? This is the pseudo inverse, right? V sigma inverse and U transpose. So that matrix is the pseudo. Let me do one example. This example will clarify everything. So I took one matrix 3, 2, 2 and 2, 3 minus 2. I'm not showing all the eigenvectors and eigenvalues that. And this is the orthogonal matrix, and this is the sigma. So, right? Sigma is this one. This is why I am choosing that A transpose A transpose whole inverse in this case. Why? Because rows are independent. In this case, I am doing two examples here. These are rows are independent. That's why we got A transpose whole inverse. That is the pseudo inverse. That is the right inverse, right? And let's choose 1 by 1, 2 and 1, 2. What is the rank of this is 1. It's not invertible. But we can split into SVD. Any matrix A m by n can be written as SVD. So this is the SVD is U sigma V transpose. I did that. What is sigma here? Sigma 1. Sigma 1 is root 10. This is perfectly invertible. This is perfectly invertible because they are orthogonal matrix. They have linearly independent. No problem. For this two-sided inverse exists. For this two-sided inverse exists. No problem at all. But this is the pseudo inverse. So I'm taking 1 by root 10. It's not inverse because it is not invertible actually, because its determinant is 0. We don't have full rank. Therefore, that is the pseudo inverse. So pseudo inverse is V sigma inverse and U transpose. That is the pseudo inverse of that. So do I have time, sir? Still?
Yes, sir. You have time.
Yeah.
Okay.
So let me see that. There is one more important topic in linear algebra. That's the I'm ending up that pseudo inverse, left inverse, right inverse projection matrices, linear regressions. How we are connecting linear regressions to the projecting onto the column space of A, projecting onto the null space of A transpose. If you are doing null projecting onto the null space of A transpose, we are getting the error vector. Projecting onto the column space of A, we are getting the projection matrix. All we did that through some examples. And What is this householder transformations in QR decomposition? So householder transformation, this is another new topic I took, because this is in numerical linear algebra. So we are finding A equal to QR. Q is orthogonal matrix and upper triangular matrix. So what is that? Q into R. Let me quickly go through that. I am finding some sequence of householder transformations. We will get up into upper triangular matrix. That I will show. What is that? So X belongs to Rn and X is not equal to 0. I am choosing some I minus 2x x transpose by x transpose x, right? See that A transpose by A transpose A, again, projection matrix. But we are taking 2 times. One more time. H is a householder transformation. The same thing we have very earlier in the one-dimensional projection, A transpose by A transpose A. See that it's a number, it's a matrix. Simply it's a projection matrix. We are taking 2 times of projection matrix, I minus 2p. What is that? What is this doing? So the key idea behind this is a reflection in 3 dimension as being a linear transformation. So how can we write a reflection into a linear transformation? So let's take a subspace, and that subspace is controlled by this normal, right? Controlled by this normal. Let me explain. The 2 vectors u bar is and x bar is here, but x bar is perpendicular to the subspace. X bar is perpendicular to the subspace. So I am projecting onto the subspace, and I'm extending that projection to that, because extending the same projection onto the. So this vector minus. Oh, okay. Let me see that. What is that? The main aim is to come up with a matrix which performs the transformation reflection along to the subspaces, right? So this is the mathematical idea. So that is the simple diagram, geometry diagram. We did that because this is the subspace, this is the one vector. Earlier we took this vector as b bar and we are projecting onto the subspace. Same thing we are doing into double the time. The projection is 2 times we are doing, therefore we are getting the reflection, right? So what is that? Let me see that. So this vector plus 2 times of that, 2 times this up. What is this vector? What is this x? How can we do that x value? We are projecting u onto the x. That is x transpose, because I took x equal to length of x is equal to 1 here. Length of x equal to 1 here. Because of that, I am not getting that bottom one is x transpose x. For my convenience, I am taking that x is in a unit vector. So this is x transpose u, and because of that direction, I am multiplying with x. It's a x transpose u is just a dot product and multiplying with x. So the same vector here we are flipping, right? The same vector we are flipping here. So that is what minus x transpose ux. This is also minus x transpose ux. Therefore, 2 times. So u minus, I am adding these 2 vectors to get this. What is this? That is the reflection. U minus 2x x transpose u. Take u common, I minus. That is the reflector. We call it as reflector or householder transformation. There is a it is coming from projections only. It is coming from projection. It's an extension of projection. Yeah. So is the H is symmetric? Yes. Do some math algebra here. I minus 2x extra. Let me. I think I have little bit time. Let me see that. H is orthogonal. If you do that, H transpose H is equal to I. I'm not doing all this math now. So H transpose H is equal to H square. H is what? I minus 2x X transpose H. Because the one thing we have to be in mind is X transpose X is not a matrix, it's a length. So it's a number. This is a matrix. So do that multiplication, you will get into I. H transpose H is equal. So householder transformation is orthogonal. That is one condition. The whole idea, householder transformation. What householder transformation? If I am applying the vector which is on the subspace, we will get the same thing. If we are doing perpendicular vector, we will get minus x. Is that correct? Because it has to reflect, right? The whole idea is some transformation is reflecting through the subspace. That's the whole idea. So this is the subspace. If I'm multiplying with h times of x, let me go to the basic here again. 1 minute. This is the h. This is the householder transformation. That makes the u vector into the another vector. It reflects through the subspace. So if x is perpendicular, hx is equal to minus x. If it is y on the subspace, it will give the same vector. What is the condition here? So householder preserves their length. It won't change length because reflectors will not change the length. So that is the whole idea behind this. And there are some geometry and algebra I wrote here. Algebra is, so HU is equal to V. So I have some vector U. I want to reflect to my choice vector V. So X, what is the best choice here? What is the main vector here is the X bar, right? The whole transformations, let me go back. Yeah, whole transformations works on X, not on U. The whole transformations works on X. So this normal is the very important in doing this householder transformation. Let me go back. Yeah. So what is the best X to reflect U to V? I'm having two vectors. I want to reflect U to V, but what is the best X? Okay. So this is the X, right? But X and W are having the same direction. So V plus W is equal to U. V plus W, see that? V plus W is equal to U. So W is equal to U minus V. So I got this vector is U minus V. Therefore, multiply with its length, you will get the unit vector, right? So that's the idea. So what is the best choice to do the householder transformation? U minus V. If I am vector U, I want to reflect to the V. What is the best choice to prepare a householder transformation is U minus V. So let's do that through algebra also we can do, but not necessary, I think. You will end up with the same thing with algebra also, because H is I minus 2x X transpose, and U, in place of U I am writing U minus V. Do some algebra, you will end up with V. See, the geometry and algebra is giving the same conclusion. So householder makes U to V, best choice is U minus V. This is the key idea. So I'm having U vector is first column of matrix. I want to target to this matter. This is the, what is this? This is the identity. This is the one of the basis vector for the Rn, right? So I want some householder transformation, which makes this one like this. So what vector I need to use from this concept? What vector we have to use? That minus that, right? So first column minus that. So see that? But the condition is length of U and length of V is the same, because it's a reflector. The householder transformation is doing the reflection. So I'm taking the length of U equal to length of V. What is length of V is alpha. So V is equal to alpha E1. So U minus V, right? V is, one more time. So U is, length of U is equal to length of V. Length of U is what? First column length. Square root of A1 1 whole square, A2 1 whole square, A3 1 whole square, something like that. We will get that alpha. Because that length and that length are same. Alpha equal to the square root of these squares of these entries, right? So x is equal to U minus V. This is the first column. V is this length times E1. So I got the two choices. X is this and that. So which one you have to choose for the householder transformation? Based on based on the sign. Which sign we have to use to avoid the cancellation? If I'm A11 is greater than 0, use plus sign. So I got one vector x. So with that x doing this I minus 2xx transpose, I will get the householder transformation. That householder transformation I am applying this matrix, it will become 0, 0, 0, right? Because it keeps the first, that is the whole idea. It keeps the first value and remaining are 0, 0, zeros. Why that is so helpful? Let me explain one example. So I am taking this and I am targeting to this 1, 0, 0 because I want R. The whole idea is making into the upper triangular matrix, right? A times some householder transformations is equal to R. So A is equal to multiplying the householder transformation. First householder transformation makes like this, and take this one, do the second time for that. So this is the first column, target is that. So take the U minus V, that vector, apply that householder transformation, you will get that. See, it makes into upper triangular matrix. So R is equal to A is applying 2 times of householder transformations. We will end up with upper triangular matrix. That is your QRD composition. This is developed based on the projections. That's the whole idea of this lecture. Thank you for giving me the opportunity, and thank you all.
Thank you, sir. For your lecture on applications of linear algebra, matrices and least squares. And this is the time for question and answer session. Because of huge participants, any participant who is interested to clarify their doubts, please come forward to post it in the chat box. Sir will clarify the same. Dear participants, if you have any doubts, please post in the chat box. Sir will clarify the same. And there is one question, sir. How to check stability or convergence of projection matrices? One of our participants requested how to check the stability or convergence of projection matrices.
The projection matrices are projection matrix is the near, it's making to the nearly identity but not identity. So we are bringing that whole vector into the column space, right? But it's not an identity. In some cases it will become an identity if all vectors in the columns are having the full rows or full columns are linearly independent, then we will get the identity matrix. If all columns are fine, if I'm choosing one vector, that's fine. Ax is equal to b is solvable, no problem at all. If b is not in the column space, we are bringing that b into the column space of A, but not identity will give. But it is trying to become an identity. It is trying to become an identity forcibly. That's the called convergence. It's not identity. It is trying to become an identity in the column space. If you are projecting into the row space, you are becoming it's a identity into that row dimension. I think so.
Pawan Kumar sir.
Sir, thank you, sir.
You have delivered an insightful session on linear algebra, sir.
Thank you, sir. Thank you so
Clearly
much.
explained key concepts such as orthogonality, projections, and Gram-Speed process. No doubt, sir. The session is highly enriching and demonstrating how linear algebra enhances model performance and deepens our understanding. Wonderful, sir.
Thank you so much, sir. Thank you for giving me the opportunity.
Sir,
And thank you for
Karunakar,
the
sir.
audience too. Thank you for the audience too.
Karunakar, sir, please go ahead, sir. Sir, please unmute your audio, sir, please. Karunakar, sir, please unmute your audio. It is not audible. Yes, sir, please.
Thank you, one and all, for your great response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with a vote of thanks by our co-convener, Dr. T. Srinivasrao garu. Dr. T. Srinivasrao garu will present vote of thanks.
Good evening, everyone. On behalf of the Department of Mathematics and all participants, I wish to extend my sincere gratitude to today's speaker, Dr. C.V. Pavan Kumar Garu, for his insightful presentation on linear algebra. Dr. C.V. Pavan Kumar Garu has discussed the basics of linear algebra like orthogonality of vectors, orthogonal projections, and the Gram-Smith process. These ideas are connected to practical applications in machine learning, particularly the method of least squares for fitting lines to the data. Also, C.V. Pavan Kumar Garu has demonstrated how linear algebra provides the mathematical foundation for optimizing models, reducing errors, and improving predictive performance. Today's session is truly enjoyable and is enlightening us how to use linear algebra to expand knowledge within the teaching community. Dear participants, you are all informed that feedback link has been shared both in the WhatsApp group and YouTube channel. It will be opened till 7 p.m. today. All of you are requested to fill the feedback form within time. Thank you, one and all. Thank you, Pavan Kumar Garu.
Thank you, sir. Thank you. Thank you. Thank you, Achal garu. Thank you so
Sir,
much.
thank you. Thank you very much, sir.
Thank you, sir.
Thank you, sir. Thank you, Pavan Kumar garu.
Yeah, thank you, sir.
Vinod.